Section 1.7 deals with reliability of measurements, and I actually had a version of this graphic way back when I was going through undergrad, and I always thought this was really something that stuck in my mind and really kind of highlights this point about how reliability of measurement is not just something that we torture you guys with in terms of significant figures and your lab calculations and that sort of thing. The reliability of measurements, in fact, is probably one of the most important aspects of a measurement. And why is it the most important part? Well, just think about this. What good does it do me to say that something is 20 miles away if the reliability of that measurement is plus or minus 20 miles? Right? It could be right next door, or it could be 40 miles away. You know, if I know that the mass of a particular bag of apples, for instance, is 3 pounds, but that's plus or minus 2 pounds, that's not real helpful. 1 pound or 5 pounds or somewhere in between, that doesn't really help me to understand the actual situation or system that I'm looking at. So in a way, a number that you don't know for sure, that you don't know in any reliable way, is pretty much a useless number. So let's take a look at this. When I present data as a scientist, I'm going to present it in a very specific way, and that way is going to indicate to the people reading it what level of reproducibility and what level of precision and reliability I am trying to get across with that particular number. So for instance, in this data, the amount of carbon monoxide concentration in the atmosphere in different years from 1990 to 2010, I'm showing 8.9, 6.2, etc. I'm showing a ones digit and a tenths digit. What that's implying to somebody who's looking at this is that this is known to plus or minus 1 in the last digit shown. So that means that we know the 8 for sure in this first row, and the 9 fairly sure, but it's a little bit of an estimate, or we're a little uncertain of that last digit. It's plus or minus 1 in that particular column. So all of these numbers have about the same level of reliability. They're all reliable within plus or minus 1 in the tenths place. Now if I reported this differently, I reported this as just ones column digits, then what I'm trying to imply by this particular way of reporting the data is that this is plus or minus 1 part per million. That's the units that this table is in, so that the reliability of this measurement is actually a lot less than if I showed the data in this way. So only the person measuring it has a good indication right off the bat without having these other external cues to the reliability of the measurement. So you have to transfer that information about reliability across in some way. And this how many digits am I going to display idea is one of those ways to convey reliability of a measurement. So let's look at reported digits. So if I have 3.182 grams of carbon as a measurement that I've made, what I'm trying to say here is that I have measured reliably the 3, the 1, and the 8. I am not uncertain of those at all. Those are in fact certain digits. What I am trying to get across though by stopping here at the thousandths place, this 2 and this third decimal point over from the right, is that this 2 is actually the uncertain digit of this measurement. So that uncertain digit means that I am again indicating that I am plus or minus 1 in that particular value. So this measurement of carbon could be seen as 3.182 plus or minus 0.001 grams. So just as we'd expect from seeing a number that's reported to this many decimal places, this is a pretty certain measurement of the mass of carbon that must be present. So for each of these, tell me what's the estimated digit and what's the plus minus value associated with each of these measurements. So go ahead and pause it. come back. All right, so again, we have 1, 2, 3, 4 certain digits, or significant digits, as they're sometimes called. Significant figures, or digits, and 1 uncertain digit. So when I count these all up, I am going to say that I have the 4 certain digits plus the 1 uncertain digit, giving me a total of 5 digits that I'm going to have to contend with in a calculator. Okay, so that digit that's estimated in this case is that last one, that's the 4. So this measurement is going to be plus or minus 0.0001. Okay, so the estimated digit is that last 4. So again with this number, how many significant digits do I count in this particular number? Well, there's 2 certain ones, and then we have the 1 uncertain. So that's 3 significant figures that I will have to keep track of for a calculation. But the estimated digit is always the one farthest to the right here. So this is the uncertain digit, meaning that this particular number is plus or minus 0.1. And it's pretty straightforward when all I have is these just numbers that are present and there aren't any zeros or anything like that that I have to contend with. When I start adding the zeros, it gets a little bit more complicated, which we'll see in a little bit. Okay, so if I'm making a measurement, if I'm measuring a liquid or I'm measuring something with a ruler, I have to take a look at what the level of reliability is for what I'm using to measure. So for instance, in this graduated cylinder, I'm going to look at, we have this kind of curved shape to a liquid that's present inside of that container. And that's because things that are polar liquids actually like to kind of creep up the side of the glass here. They kind of creep up on both sides. So we measure at the bottom of this meniscus. That's the curvature is called a meniscus. So where does that fall? Let me get rid of all this ink that I just put all over here. There we go. So if we look at this, the bottom of the meniscus falls right about here. All right. Well, if this big number corresponds to 4, and this is in milliliters, so that's 4 milliliters, and each of these other lines, which there are 10 of, must be tenths of a milliliter, then I know I have at least have 4.5, and I know the meniscus is under, this big line's 4.5, I know it's less than 4.6, so I know for certain it's at least 4.5. Okay, so these are certain digits. What I have to then do is estimate how far between the 0.5 and the 0.6 this particular meniscus falls. So I'm going to say, I'm going to go out on a limb and say it's a little bit more than halfway. So I'm going to say it's about 6 out of 10 spaces between the 0.5 mark and the 0.6 mark. So that's the digit that falls into the hundredths place here. So I'm going to say it's about 4.56 milliliters. Okay, so you're looking at this and you're saying, okay, yeah, it could be 4.56, but I think it's a little bit closer to maybe 4.57. Or some people might look at this and say, maybe it's a little closer to 4.55. That's very valid, because this last digit, just like in all the other measurements that we were looking at before, is the uncertain digit. We're saying that we're sure about the 4 and the 5, but that last digit, that's another story. That we're going to not be quite as certain about, and that's conveyed by writing down this measurement as 4.56. People will automatically know by reading that that last digit is the uncertain one, and that we're actually considering this to be plus or minus probably about 0.1 milliliters. Okay, so you guys do this one. Take a look at it, kind of mentally draw a line here and see exactly where you think this is. Pause. Alright, you're back. Alright, so if we kind of draw a straight line, oh, that's not the straightest line in the world, but there we go. Where does this fall? Well, this is 90. This is 100. And this is 110. So that means it's more than 100, less than 110, and there's 10 lines between. So this must be 101, 102, 103. So it's right around 103. And we're absolutely positive it's not 102, and we're absolutely positive it's not 104. So the 100 and the 3, we are absolutely certain of. There's marks for those. What we are estimating is, did I draw this straight enough, or is it a little bit past 103? Maybe it's a little bit less than 103. But we're going to say, in this case, it's right on that 103 line. So the one that we're guessing is right here. So we're certain about the 1, the 0, the 3, but we are maybe plus or minus 1 on this 0 here. It might actually say be 102.9. Might be 103.1, but this is our guess as to the temperature. It's a thermometer, so the units are degrees Fahrenheit. Okay, so when we start counting significant digits, we're going to need to do that sort of thing in order to figure out how to assign significance to numbers, whether we should include them as significant in calculations or not. So let's start looking at how we would count digits. So all non-zeros are significant. That's right off the bat. The 2, the 8, the 3, definitely significant. The 5 and the 4 here, definitely significant. I'm not saying anything else isn't, but just for right now, automatically know if it's not a 0, it counts. Okay? Interior trapped zeros are significant. So not only is the 4 and the 8 in this example significant, but because this 0 is in between digits that are significant, it is also significant, meaning that this guy right here is also significant. Okay? So for this number, already we'd know we'd count 4 significant digits. In this number, we would count 3 significant digits. Here, we have a 7, a 3, and a 1. Those are all significant. We have a 0 between 2 significant digits, and another 0 between 2 significant digits. So those all count 5 significant digits. Okay? So I'm not talking about this guy yet. Okay? That's got some zeros in front, some zeros in back. We haven't gotten there yet, so don't worry about this at the moment. 4 here, 3 here, 5 over here. Zeros that lead are not significant. All these are really here for is to show that this number is small. It's not 0.3, it's not 3, it's 0.003. So it's showing the size of this measurement. It's called the magnitude. So things that only serve to show you how big or small a number is, they're not considered significant in terms of assigning number of digits to round to in a calculation. So we know from our previous rule that non-zeros are significant, so the 3 and the 2 are, meaning that we have 2 significant figures here. So for this number, not, yes. So this value, 0.0006, is 1 significant figure. You'll very typically see this 0 to the left of the decimal point. And now, while I understand that that 0 doesn't necessarily have to be there in order for this to be a understandable number, we like to refer to this as the courtesy 0. That 0 helps us if the decimal point might be a little difficult to see, and sometimes handwriting makes a decimal point difficult to see. But because there's that non-standard space between these two zeros, it helps us to go back and look and say, hey, is there a decimal point here that I missed? Possibly. Alright, trailing zeros, zeros that occur after a decimal point. those are always significant. I didn't need to write these to show how big or small the number is. So if I do write these, I do have this written down somewhere for someone else to look at. The assumption is made that these are significant and measured zeros. So that means we have the 4 and the 5, all three of those zeros, 5 significant digits here, 5 significant figures. Same thing here, 30.5600, all 5 of those digits are significant. Okay. Trailing zeros before a decimal point are always significant if there's a significant digit after them. Okay, so 1 and 4, those are significant. Everything after the decimal point is significant. So this 0 here is kind of following that same rule of it's trapped between two other significant digits, so it is also significant. It also must have been measured. So again, in this case, we have 5 significant digits. Here again, significant digits, significant digits. These are before the decimal point, but there are significant digits to the right of the decimal point, so those zeros then are significant, meaning that we have 6 significant figures here. Now, what about if we have these trailing zeros, but we're not quite sure? They're before a decimal point, or maybe even before an implied decimal point. So with just this number right here, we're not entirely sure whether or not these zeros are measured. It's not quite clear. It's really kind of actually ambiguous. So a better way to show this number that shows us very specifically how accurately, or how precisely I should say, we measured this 1200 value is to put it into scientific notation. So don't do this. Don't put numbers with zeros like that are uncertain or ambiguous as to whether or not they're measured when the next person reads them. Instead, if I want to say that there's 2 significant figures here, I'll write 1.2 times 10 to the third. If I want to say that there's 3 significant figures, I'll say 1.20 times 10 to the third. So that 0 is now to the right of a decimal place, so that's indicating that this is a measured 0, or a significant figure. And so on here, we can do the same thing. Now, some texts, our text doesn't, luckily, but you will see this from time to time, that if someone puts a decimal point after these zeros, but there's still nothing on the right of it, they're trying to imply that those are significant zeros. But a lot of times people who are non-scientists, who are like book editors and that sort of thing, will just throw that decimal point in there even though it might not be significant. So this typically refers to 4 significant figures, but we're not going to do that sort of thing. If we need to specify, we're going to put it into scientific notation if we have to. We also have what's referred to as exact numbers, numbers that are defined. So for instance, if I say 2.54 centimeters is 1 inch. These 1 and the 2.54 are exactly 1 inch and 2.54 centimeters. So these have an infinite amount of significance. They are as many digits as we need them to be in terms of their level of significance when we perform calculations and measurements with these. Same thing with 12 inches to a foot. It's exactly 1 foot. We don't think it's 1 plus or minus 0.1 foot in 12 inches. It's not 11 or 13 inches in a foot. It's exactly 12 inches in 1 foot, or 100 centimeters in 1 meter. Another example I didn't write here, is counting numbers. If I say I have 3 oranges, I don't have 3 plus or minus half an orange. I have 3 oranges, right? And I'm going to get some kind of nebulous plus or minus a quarter of an orange or something on the end of that. So if I count a number of physical objects, and I can reliably count those objects to a specific exact number, then that count will have an infinite amount of significant figures as well. Okay, so how many significant figures do each of these have? Pause it, figure out all of them, and then we'll go over the answers. Welcome back. Alright, so leading zeros are not digits, and a digit to the right of a decimal place that's not a leading zero. So we have 4 significant figures for this number. Leading zeros, so not 1 significant digit for this number. 5, trap 0, trap 0, trap 0, 3, 5 sig figs. 1 to the right of a decimal point, so yes, yes, and yes. 4 significant figures altogether. Infinite number of significant figures, and ambiguous, so we have to assume 1 significant figure unless we know for certain that it's more than that. Alright, so here's why we had to figure out all that goofiness about how many significant figures something has. When we count significant figures, it allows us to look at where we should round our answer for multiplication and division. All we do is we count the number of significant figures in each number that we are using to multiply together, and then we use whatever the least number of significant digits in the start of a problem is, and round our answer to that many significant digits for the final answer. So for instance, if we have 1.052 times 12.504 times 0.53, what we have is 4 digits, 5 digits, and 2 digits. So this answer is going to have to get rounded to the least of that, or 2 digits. 6.7. So you try this next one. Alright, so you've unpaused. 1, 2, 3, 4, 5 digits. 1, 2, 3, because that 0 counts because it's to the right of a decimal point. It's not a leading 0. So 5 and 3, we should have 3 digits. This 0 would not count. 1, 2, 3. This is 0 here, so we round down to 0.626. Excellent. Addition and subtraction is a little bit more interesting. Here what we do is we look at it lined up so that all the place columns are in the same spot, and we start moving over from the right to the left and find out where the first column is, where every digit, every number that we're adding or subtracting together has a significant digit in it. Okay, so 0.355 plus 105.1 minus 100.5820. We add this up and get this number at the bottom, but we have nothing here or here, so we can't use this row. We have a 5 here and a 2 here, but nothing there, so we can't use the 3. 5 here and an 8 here, but nothing on the second row, so we can't use the 7. We have a 3, a 1, and a 5, so every data value here, all 3 of them, have a significant figure in the tens place, so that's where we round to. Now the numbers to the right are more than halfway up towards the next number, so that means we round this up to 4.9 because this 7 right here is greater than 5. Okay, so you practice. Pause, and we're back. Right, so 5.9 minus 0.221. Let's look at this. We have to line them up to kind of see where things fall. So 5.679. So don't have anything here. So that column's out. Nothing here. So that column's out. So we're rounding to this digit. This is a 7, so we round up. So 5.7. The 6 rounds up to 7 because of this digit here being greater than 5. And there's our answer. When we have scientific notation, the smart thing to do is to put them all in the same times 10 to the power of. And that can be times 10 to the power of 0. You can put this back as a normal number as long as the exponent isn't too outrageous. So we have 1200, 2, 3, minus 200. And the significant digits present are the 1 and the 2. And here the 2, the 0, and the 0. Okay? Because this is the significant digits we had. So that means, since this is not significant, our answer down here will not have significance in that place. Since this number is not significant, because only the 2 in the 1200 is significant, we can't use that place either. Now the 2 here and the 2 there, those line up, those are significant. So this value, 2 minus 2, will be significant. And the 1 is also significant because everything to the left is significant. So this equals 1,000, but this 1,000 is only significant starting at the hundreds place. So we have to display this with a value of 1,000, but indicating that we have these 2 digits of significance. So we're going to have to put this back into scientific notation. Okay, so to do that, it's 1 times 10 to the third. Okay, let's look at this. 120 minus 200.0. That one's not significant because it doesn't have anything to the right of the decimal place. So we have 120 minus 20.0 gives us 100.0. That's significant, but this isn't, so that's gone. This is significant, but this isn't, so this is gone. These are both significant, so we have the same thing here. It's 100, but only the 100th place and 10th place is significant. So we'll have to put that into scientific notation to make that clear. If we have order of operations, we have to kind of keep track as we go. We don't want to round early, because if we round early, we're going to end up with a different answer. So we always wait till the end to round. But all you do is just kind of keep track and try and follow the order of operations here. So you have this on the top of the fraction, so we're going to do the subtraction first. And we get 1.002 minus 0.999. So when we do this, they both have significance in this thousandths place. So this 3 is significant. Okay? Now technically, so are these zeros. All right, even though they're indicated this way, they were significant because these columns were significant. But now we're about to divide. We forget all about this stuff for right now and just say, well, that 3 is significant, but the way this is set up, I do not have any significance to these numbers. So when I divide, now I'm not going by columns anymore or by number of decimal places like I was with the subtraction. Now I'm going with just the number of digits that are significant that are present. So here we have 1 significant digit, and on the bottom we have 4. So the answer will have the least of the 2, or 1. So we're going to get 0.0008. All right, because we're going to round up in this case. Now if we want to show this in scientific notation, we have 8 times 10 to the 1, 2, 3, 4, negative 4th. So the last thing in this section, it's rather a long section, but just wait, the 1.8 is even more exciting. The last thing we have here is this discussion of precision versus accuracy. So precision is how close measurements are to each other. Accuracy is how close the average of your measurements is to the real number, or the true value. Okay? So we have a couple of possibilities. We can have this kind of scattered all over the place, not close to each other, and we're assuming we're aiming for the center of the target here. And the average, which would be about here, isn't close to the actual true center that we want, so this isn't precise or accurate. The second one, they're all close to each other, so it's precise, but the average is not where it should be, so it's not accurate. In this case, if you take the average actually hits right in the center, so it's accurate, but they're kind of spread out all over the place, so it's not a precise measurement. Here they're all tightly close together and in the right spot, so it's precise and accurate. What if we look at some data? Alright, well, we're going to say that we're trying to measure something that should weigh exactly 10.00 grams. It's the true value. So which of these are precise and which are accurate? Let's see, 10.5, 9.7-ish, 9.9, 10.3. These are kind of all over the place. And that's not very close to 10. Okay, so not precise and not accurate. All right, 3.78, 3.75, 3.80, 3.82. These are really close together. So it's precise. However, 3.79 is not 10. Not accurate. 1.03, 9.99, 10.03 again, 9.98. These are very close to each other, and the average is very close to the true value. So it's precise and accurate. Now you can see this a little better too on a graph. The blue line is the true mass. The red line is the average mass of the measurement. You can kind of see these guys are all over the place, not accurate, not precise. Here you can see these are all really close to the average. That's what makes them precise, but they're not close to the real number, the true number. And here the average is very close to the true number, and the numbers are close to each other, so accurate and precise. So what makes things not precise or not accurate? Well, systematic errors and random errors are what we're going to run into in the lab. Now, a systematic error is one that's always the same kind of error in the same direction. So a measurement that's always high or always low, that's a systematic error. Things like that could be, I'm using a scale that's off. It always measures things that's 2 grams heavier than they really are. That's a systematic error. Or I'm measuring with a beaker that has a mark on it for 20 milliliters, and in reality it's only 19.8 milliliters. That's a systematic error. Every time I use that beaker, it's going to be off by the exact same amount. Random error is, I'm trying to measure something, and I can only measure it so well. I'm always going to have some plus or minus value associated with that particular measurement. And I'm going to be off a little bit every single time, but not always in the same direction. Sometimes I'll be a little high, sometimes I'll be a little low. That's what random error is. It's not always in one direction, but sometimes high, sometimes low. So what do we do with these two types of error? Well, for systematic error, we can test a known value, some known sample, and see how close it is. And then we can correct things and account for any kind of systematic errors. If we weigh something that we know should weigh 10 grams and it weighs 9.8, we know that the scale is off by about 0.2. How do we deal with random error? We take more measurements and we average them together. The more measurements we make, the more likely we are to have enough high and enough low to kind of cancel each other out and average them out. So taking more measurements helps us to lower the amount of random error we have. No matter what, we're always going to have a certain amount of systematic and a certain amount of random error. That's unavoidable. All we can really do is try to minimize them to acceptable levels.